So now we're going to move on to what's called conditional probability. And so with conditional probability, we are going to be looking at events with conditions put on them. Given something has happened, or given this particular condition is met, then what would happen? So let's go back to our pierced ears example with that statistics class that had 178 students in it, all right, 90 males and 88 females. So if you know that a randomly selected student has pierced ears, what is the probability that that student is male? So what we're looking at here is we are looking at a probability here where conditions have been set upon us here. So we're looking at probability that the person is male given they have pierced ears. Okay? That order is going to be really important. Okay? So if you look at the question, if we know that a randomly selected student has pierced ears, what is the probability that the student is male? So you want the probability that the student is male given that they have pierced ears. You know they're going to have pierced ears. So now you want to know the probability that they are male. So when you're looking at conditions like that, like in a two-way table, then you're going to be solely focused on the group that is my given. So given that they had pierced ears, so I'm only focused on this row right here. I don't care about the other row because it doesn't meet my condition. It doesn't meet my given that they're going to have pierced ears. So given that they have pierced ears, now my total is not 178. My total is only 103. Okay, and now I want to know the probability that they're going to be a male given that they have pierced ears. That now becomes 19 out of 103. Okay, so let's look at the next one there. If we know that a randomly selected student is male, what's the probability that the student has pierced ears? Well, this time my condition is that they were a male, okay, not that they had pierced ears. So if I look at only that condition, that they are a male, I'm not looking at the female because that doesn't meet my condition there. Okay, so given that, if we know that a randomly selected student is male, what's the probability that the student has pierced ears? So given that they're a male, the probability they have pierced ears. Well, now my total becomes 90, okay, and I still have 19 males. So now I get 19 out of 90, or 21.1, which is a very different probability than my 18.4 with my 19 out of 103. So order is going to be really important when we're talking about these conditional probabilities. So our conditional probability is going to have a special notation for it. And here our notation is right here. So our conditional probability, the probability that one event happens given that another event is already known. So that makes it a conditional probability. Okay, we know that event A has happened. We know that they were male, or we know that they had pierced ears. Then the probability that event B happens given that A has happened. Okay, so when you're writing this notation, so if I write the probability of event B given that event A has happened. So this line in the middle here, that represents our given that portion. So we don't have to keep writing that. Okay, and then you will also need to make sure that you've defined events A and events B. For example, in the last example that we just did, we want has pierced ears given that they're male. Okay, and so our events in that particular case were, let's see, A was that they were male, right? And the probability of event B was that they had pierced ears. So if I want has pierced ears given that they are male, I can then write now B given A because I defined what those were. And so that now says the probability that they have pierced ears given that they are a male, okay, which would look like what we did before, right, where we had 90 males, 19 of them. So let's look at the formula for calculating these. Okay, so our formula for calculating these, let me get rid of all this. Okay, so here's our formula. So our formula, given the condition, so the probability that event A occurs given event B, you use your formula here. Okay, so they're both going to be the same, right? We've got our intersection there, the probability of A and B occurring, over the probability of our given event, probability of B. If we're switched here and we have the probability of B given A, then the probability of event A goes on the bottom, right? So our given event always goes on the bottom, and then the probability of the intersection of the two events goes on the top. On your formula sheet, you only have this one right here, but the formula you'll notice is the same. You just need to realize that the given event is the one that goes on the bottom. Okay, but you only get one version of the formula, which is this top one here on your formula chart. This formula, I think, looks a little bit intimidating. Don't let it freak you out. You'll notice we already did an example, and we used these formulas, right? The 19 over 90, the two events occurring over the given. Okay, so it's not as scary as it looks. Okay, so let's look at an example here. Let's go back to, this is the newspaper example from before. The residents of a large apartment complex based on events A, that they read USA Today, B, they read the New York Times. The completed Venn diagram is reproduced there. So here's your Venn diagram again there in the middle. Remember we had the 0.05 that read both, the 0.2 that read the New York Times, the 0.35 that read USA Today, and 0.4 that read no papers at all. So what's the probability that a randomly selected resident who reads USA Today also reads the New York Times? Okay, so what we have going on here is we're looking for the probability that somebody who reads USA Today, so that's going to be my given, right, that they read USA Today. So I want the probability, given that they read USA Today, they're also going to read the New York Times. So that's how I define what I'm looking for there. I'm looking for the probability that they read the New York Times given that they read USA Today. There's my given symbol there. If you look at your exam tip over here in the corner, it will say that I could have written the probability, because my events are defined up here, I could have written this as the probability of B, which is them reading the New York Times, given they read USA Today. I could have written it that way because I defined my events. If I had not defined my events, then I can't write it that way, and I have to write it this way, the long way. So it doesn't matter which way you do it. Either way, you're going to be defining your events. You just need to decide which works best for you. Do you prefer this notation like this, or do you want to just go ahead and write it all out in the parentheses there? So based on our formula, right, our formula would be the probability of B given A is going to be equal to the probability of the intersection of the two over my probability of event A, because that's my given condition there. Okay, so if I want to determine what this is, I'm going to have 0.05, that's my intersection, over my probability of event A, which is that they read USA Today, and that is going to be 0.4. It is not 0.35. Let's go up to our diagram here. Reading USA Today is this entire yellow circle. So these people that read both also read USA Today. So I need my total from the whole circle, which is 0.40. So 0.05 over 0.4, which gives me 0.125, which is my probability that a randomly selected resident who reads USA Today also reads the New York Times. So there is a 12.5% chance that a randomly selected resident who reads USA Today also reads the New York Times. So we're going to have to also practice, saying these in context. I can't just give this and be done. I need to explain what that 0.125 means. Okay, let's look at another example. Students at the University of New Harmony received 10,000 course grades last semester. The two-way table below breaks down these grades by which school of the university taught the course. The schools are liberal arts, engineering and physical sciences, and health and human services. Let's see, the table is based closely on grade distributions at an actual university, simplified a bit for clarity. College grades tend to be lower in engineering and physical sciences than in liberal arts and social sciences, which includes health and human services. Choose a University of New Harmony course grade at random. Consider the two events E. The grade comes from an EPS course, and a liberal arts, and L. The grade is lower than a B. So your events are defined. Consider the two events. E, the grade comes from an EPS course, and then L, the grade is lower than a B. So your events have been defined for you. So number 1 is asking you to find the probability of L, and then interpret this probability in context. So this just wants the probability that the grade is lower than a B. This is not the probability. There's nothing given here. There's no conditions set on this probability. So this is going to be a probability of L is going to equal my total here of grades below a B. So 2,268 plus 800 plus 588 over, there were 10,000 grades in total. Okay, which is going to give me 0.3656. And then I'm not done. I have to do the interpret part. Interpret this probability in context. So if I'm going to interpret this probability in context, there is a 36.5% chance of randomly selecting a course grade that is lower than a B. Okay. That's what I'm looking at here. That's my context. So there's a 36.56% chance, or there is a 0.3656 probability of selecting a course grade that is lower than a B. So that's my interpretation there in context. Again, it could also say there is a 0.3656 probability. And let's look at number 2. So number 2 has some conditions put on it. Find the probability of event E given event L, and the probability of event L given event E. Which of these conditional probabilities tells you whether the college's EPS students tend to earn lower grades than students in liberal arts and sciences, and explain. So let's clear out some space here. Okay, so I want the probability of, let's start with the first one there, the probability of E given L. And I can write it like that because my events are already defined for me. So on the bottom, I'm going to put my given, which is going to be the probability that the grade is lower than a B. Okay, well, the occurrence of grades lower than a B. So 3,656. And then I want my intersection of grades that come from an EPS course, and the grade is lower than a B. So that intersection on my two-way table happens right there, which is 800. The reason why we put the 3,656 on the bottom is because this was given to us in number form, not in probability form. So I would have had to calculate this probability here, or I can just realize that my probability was 0.3656 of event L, and I had 10,000 grades, which would mean 3,656 of them should be lower than it, or would be below a B. So my probability of E given L here is 800 over 3,656, which is going to give me 0.219. My probability of event L given event E, so this time I'm putting my probability of event E on the bottom. Okay, and so engineering and physical sciences. So I have 368 plus 432. 368 plus, here, let's go over here with this. My probability of E, right, is going to be 368 plus 432 plus the 800 all over the 10,000, right, which is going to give me, plus 800, right, which is going to give me a 0.1600, which would translate into 1,600 grades. So my probability of event E, I've got 1,600 grades. That would be event E. And my probability of L, my intersection of L and E is still 800. So 800 over 1,600, which gives me 0.50. So now I have my two probabilities, my 0.219 versus my 0.50. So the second part of my question, which of these conditional probabilities tells you whether the college's EPS students tend to earn lower grades than students in liberal arts and social sciences, and explain why. So the probability of L given E, so our second one there, gives the probability of getting a lower grade given that the student is studying engineering or physical science. So my probability that they're going to get a lower grade given that they're in engineering or physical science is much bigger than my probability that they're going to, that they are studying engineering and physical science, given that they are getting grades that are lower than a B. Because that's what my first probability says, right? My first probability says that given that their grade is lower than a B, then what's the probability that they're studying engineering and science? Where my second probability here tells me, given they are studying engineering and science, what's the probability that they're going to get a lower grade? So because the probability is 0.5, okay, it's greater than the probability of them getting a lower grade, which was just 0.3656. So it's greater than that probability. So we can conclude that grades are lower in engineering and physical sciences. If they weren't lower, then the probability would be the same. If the grades weren't lower in those engineering and physical sciences, then the probability of them getting a low grade, given that they were in engineering and sciences, should be the same as the probability of all of the students getting a grade below a B. So it should have been 0.3656. But since it's not, okay, we can then conclude that the grades in engineering and physical sciences are lower. Okay, so let's look at another rule here. So we have our general multiplication rule. So the probability that events A and B both occur can be found using the general multiplication rule. So I want the probability of events A occurring and event B. Okay, and so we've got our formula here for it. So the probability of A and B, which is the intersection of A and B, because so far that's been given to us. It's been given to us in our examples, in our two-way tables, and our Venn diagrams. So how do we solve for that? So the probability of A and B is our intersection of A and B, and that's equal to the probability of A times the probability of B given A. Okay, and so the probability of B given A is the conditional probability that event B occurs given that event A has already occurred. Let's look at kind of how that would work here. Right, so if we go back to our formula for conditional probability, right, the probability of B given A is equal to the probability of the intersection of B and A over the probability of event A. Okay, I want to be able to solve for this right here, okay, because the probability of B intersecting A is equal to the probability of A intersecting B. Okay, so even though this one says A and B, that's equivalent to the probability of B and A. So I want to isolate that, just like I would in any other math class. So when I go to isolate that, now I get the probability of A times the probability of B given A equals the probability of B intersecting with A. And so I can get that multiplication rule that looks kind of crazy up there. Okay, and so it's really going to just be about keeping your notation correct and paying attention to what conditions were set. Okay, so let's look at an example with this. So what I have here is the Pew Internet and American Life Project find that 93% of teenagers ages 12 to 17 use the internet, and that 55% of online teens have posted a profile on a social networking site. So find the probability that a randomly selected teen uses the internet and has posted a profile. Show your work. Okay, so what this wants me to do, basically it's saying that two events have to occur, and the first one must occur, and then given that that first one occurred, the second one has to occur. So I want both of these events to occur. So I want to find the probability that a randomly selected teen uses the internet and has posted a profile. So to do that, okay, I know, let's go ahead and kind of define some events right here. The fact that the probability that they're online, okay, use the internet is 0.93, and then the probability that they have a profile given that they're online. Okay, because you'll notice there it says that 55% of online teens. If they're not online, they can't post a profile. So the probability that they have a profile given that they're online is 0.55. Okay, so if I want the probability that they are online, so a randomly selected teen uses the internet, and, okay, remember that's what my intersection there is and. So they're online and they have a profile. That is going to be equal to my probability of event A, right, which is online, right? My probability that they are online times, and I'm going to ran out of room, but you get what I mean, right? Probability that they have a profile given that they are online. So this would be equal to 0.93 times 0.55, which is going to be 0.5115. So what that would mean in context is that there is a 51.15% chance that a randomly selected teen uses the internet and has posted a profile on a social networking site. Okay, so before we did our probability simulations, we were setting up our sample space and we'd write out all those die or list all the possibilities of flipping the coin. Okay, well, sometimes when we do these series of outcomes, like I need this to happen, and then I need this to happen, and then I need this to happen, it helps to have a different way to lay it out. And the tree diagram is one of my favorite ways to kind of lay that out. Like first this thing needs to happen, then this thing could happen, then this thing could happen, then this thing could happen, and we can keep going from there. So let's look at our example that we have here. Tennis great Roger Federer made 63% of his first serves in the 2011 season. When Federer made his first serve, he won 78% of the points. When Federer missed his first serve and had to serve again, he only won 57% of the points. Okay, suppose we randomly choose a point on which Federer is served. So let's take a look at what this tree diagram shows us. So this tree diagram, so up in the context there, it told us that he made 63% of his first serves. So basically, he either makes the serve or he doesn't, right? Because those are my only options, right? So if I know that he makes the serve 0.63, right, my probability of him making the serve is 0.63, then 0.37 is going to be that he misses it because those would add up to 1. Okay, so now then it said that if he, when he made the first serve, he won 78% of the points. Well, he only has two choices here. He either makes the point or he doesn't. Okay, so 0.78 times he makes the point. So the rest of the time, the 0.22, he doesn't win the point. It said if he missed his first serve and had to serve again, he only won 57% of the point. So on the missed his first serve branch, he wins 0.57 is his probability of winning the point if he missed his first serve. So the other 0.43 is the probability that he does not win the point. So let's look at some questions and kind of ways we could use this thing. So, well, let's look over here. So if I wanted, so what this branch up here tells me, and so that's, I'm following here, making the first serve and winning the point. That's what I'm following here. So his probability that he makes the first serve and wins the first point, and wins the point. So I want both of those things to happen at the same time. So since I need both of those things to happen, I can use that multiplication rule. I can take my 0.63 times 0.78, and I get my 0.49. So he's a 0.4914, or about 49% of the time, he makes his first serve and he wins the point. Okay, let's look at another branch here. So if I want him to make the first serve, but then he doesn't win the point. So he makes his first serve, but he doesn't win the point. So I want those two things to happen at the same time. Again, I multiply them. So he has about a 13-14% chance that he makes that first serve, but he doesn't win the point. Okay, what if he doesn't make the first serve, but he still wins the point? Right, so now I want both of those things to happen. So he misses his first serve, wins the point though. I want both of those things to happen at the same time, so I'm going to multiply them. So I get a 0.2109, or about 21% of the time that happens. Okay, or he could miss his first serve and not win the point. Okay, so again, so I'm multiplying. I want both of those things to happen. Remember, the more events I want to happen in sequence, the less likely they are to happen, because I need a lot of things to be happening in particular order. So if he misses that first serve and doesn't win the point, he has about a 16% chance, or a 15.91% chance of not winning the point. I could then combine these. What if I just wanted to know the probability that he makes, that he's going to win the point, regardless of what happens with the serve? Or what if, let's see, what if, or I could calculate the probability that he's not going to make the point at all. So let's say I wanted to calculate the probability that he wins the point, okay, regardless of the serve. So either way, he's going to win the point. It doesn't matter if he made the serve or he didn't make the serve. So I could add those together, and I get 0.7023. Okay, I can add those things together because those two outcomes are mutually exclusive. Okay, he can either make the first serve and win the point, or he can miss it and win the point. He can't do both of those things at the same time. So I can just add those probabilities together. So basically 70% of the time when he's serving, he's going to win a point. Okay, so let's look at another example of this real quick. Okay, video sharing sites led by YouTube are popular destinations on the internet. Let's look only at adult internet users aged 18 and over. About 27% of adult internet users are 18 to 29 years old, another 45% are 30 to 49 years old, and the remaining 28% are 50 or over. The Pew Internet and American Life Project finds that 70% of internet users aged 18 to 29 have visited a video sharing site, along with 51% of those aged 30 to 49. And 26% of those 50 or older. Do most internet users visit YouTube and similar sites? So the problem here, suppose we select an adult internet user at random, draw a tree diagram to represent this situation. Okay, so I didn't want to get this super messy drawing with my fingers, so I went ahead and I pulled the picture of it. So let's look at what we've got going on here, right? This time we had three choices, right? They were in three different age groups. Right, so three possible age groups that they could be in: 18 to 29, 30 to 49, and 50 plus. Okay, and these are adult internet users, right? So, and then from there, I took my age groups, and they either visited video sharing sites or they did not. Okay, and I assigned my probabilities on those various branches of them either visiting or not. So find the probability that this person has visited a video sharing site and share my work. So I want the probability that they visited a video sharing site. So let's kind of lay out what that would look like, right? I need to define that. Video sharing site. And that would equal, basically that's this branch, this ending branch, this ending branch, and this ending branch. So I would need to do, I've got 0.27 times 0.7 plus because these events are mutually exclusive, so I can add these together. 0.45 times 0.51. That font is hard for me to read. Okay, and then plus 0.28 times 0.26. Okay, when I plug all that in my calculator, that is going to spit out 0.4913. So what that means is about 49% of adult internet users have visited a video sharing site. So part B then says us finding the probability that this person has visited a part C. Given that this person has visited a video sharing site, find the probability that he or she is aged 18 to 29 and show my work. Okay, so I'm going to write this 0.4913 right here as our answer to B because we're going to need it in just a second. Okay, so let's clear out some of this. 0.4913. Okay, so we want the probability, right, that they are that they have visited a video sharing site. That given that they have visited one, find the probability that he or she is aged 18 to 29. So I want the probability that they are 18 to 29. Whoops, I need that to be a straight line. Given that they have visited a video, we're going to abbreviate this, sharing site. Okay, and so remember our formula for this is going to be the probability that they visited a video sharing site is going to be on the bottom, right? And that probability we calculated as 0.4913. So all these probabilities here added together. Right, and then we want to know that the probability that they are 18 to 29. Well, and again, it's given that they visited a video sharing site. So that's really going to be on the top right. I'm going to have my 18 to 29, the probability that they are 18 to 29, okay, and, so my intersection there, and visited the video sharing site. That's going to go on the top there. And so that probability is going to be the fact that they are 18 to 29 and visited a video sharing site, which is 0.1890, right? I would multiply the 0.27 times 0.7. Okay, and that will give me a final answer of 0.3847. So what that means is that given that the person visited a video sharing site, there's the probability that they are aged 18 to 29 is approximately 0.3847. Okay, so I think we're going to stop there and do more examples in class. So you've seen a few examples of these things. So we'll do some more examples of class, and then we'll wrap up with independence, and we'll be done with this portion of probability.